Hello friends, I welcome you in lecture number 23 on hypothesis testing. In lecture number 22, we have seen hypothesis test for population variance and we have discussed how we can conduct chi-square test for population variance. So what we have discussed in lecture number 22 is that suppose we are considering a random sample of size n from a normal population, and suppose population variance of that normal population is sigma square, then if we consider this random variable n minus 1 times capital S square, which is the sample variance of that selected sample, divided by sigma square, then this random variable follows a chi-square distribution with n minus 1 degrees of freedom. So we are going to use this n minus 1 times S square over sigma square as our test statistic for chi-square test about population variance. Today we will discuss this example on how to conduct chi-square test for population variance. So in short, we are going to test the hypothesis that population variance is equal to some hypothesized value against the three possible forms of alternative hypothesis. So let's understand what is this example is saying. The lapping process, which is used to grind certain silicon wafers to the proper thickness, is acceptable only if sigma, which is the population standard deviation of thickness of dice cut from the wafers. If this population standard deviation of thickness of dice cut from the wafers, if this population standard deviation is at most 0.50 MIL, then this lapping process is acceptable. Use the 0.05 level of significance to test the null hypothesis that population standard deviation is 0.50 against the alternative hypothesis that population standard deviation is bigger than 0.50 if the thickness of 15 dice cut from such wafers have a standard deviation of 0.64 MIL. So here our parameter of interest is thickness of dice cut from the wafers, and they are saying that the lapping process is acceptable only if the population standard deviation of thickness of dice is at most 0.50. That is, lapping process is acceptable is value of sigma is less than or equal to 0.50. That is their claim, and here we have to consider 0.05 level of significance to test the null hypothesis that sigma equal to 0.50 against the alternative hypothesis that population standard deviation is greater than 0.50. And to test this null hypothesis, they are considering this sample of size n equal to 15, which is having sample standard deviation as 0.64, and here they have already set null and alternative hypothesis. They consider null hypothesis as sigma equal to 0.50 and alternative hypothesis as sigma greater than 0.50. Level of significance is 0.05, and this 0.50 will be used as population standard deviation. Now to use chi-square test, we must have normal population, or the population from which we are considering a sample must follow a normal distribution, but they have not specified anything about the population. And to use chi-square test, first thing we have to assume that underlying population is normal. So here, because it is not given in the question that population is normal, we can assume that underlying population is normal. Assume that underlying population is normal, so that we can use that chi-square test. And here we can write down whatever is given that they are considering a sample of 15 dice and sample standard deviation is 0.64, alpha is 0.05, and null hypothesis is also given. Null hypothesis is H naught is population standard deviation is 0.50, and alternative hypothesis is population standard deviation is greater than 0.50. That means we have upper or right tailed test. We have to consider area of alpha equal to 0.05 in the right tail, and this we will consider as value of population standard deviation in our formula of test statistic. So we assume that null hypothesis is true and we are testing this null hypothesis. Assume that H naught is true, alpha is 0.05, and now we can find out value of test statistic. So now, because underlying population is assumed as normal, test statistic will be given by chi-square equal to n minus 1 times s square divided by sigma square, and we are having all these values. We have s equal to 0.64, n is 15, and we will consider this as sigma. So we can substitute all these values here. So therefore chi-square is n equal to 15. So I am writing 15 minus 1 here. Then value of sample standard deviation is 0.64, and here we have square of sample standard deviation or sample variance. Sigma is 0.50, so here I write 0.50 square. So this becomes 14 times square of 0.64, which I calculate as 0.4096 up to 4 decimal places, and as square of 0.5 is 0.25, and if we do calculations up to 4 decimal places, this turns out to be 22.9376, and if we round off up to 2 decimal places, then this becomes 22.94. So therefore value of test statistic is 22.94. So this is calculation or computation related to test statistic. Because underlying population is assumed as normal, we can say that this random variable n minus 1 times s square over sigma square follows a chi-square distribution with n minus 1 degrees of freedom. Next step is to decide critical values. For that we will require degrees of freedom. So here degrees of freedom is equal to sample size minus 1, and sample size is 15. So we have 14 degrees of freedom. Level of significance is given as 0.05, and we have upper tailed or right tailed test. So first we roughly sketch the graph of chi-square probability density curve. We are familiar with chi-square distribution now. It is always negative and its graph is having positive skewness towards the right hand side. So suppose approximately this is the graph of chi-square distribution, and we are interested in the upper tail here. So this is upper tail, and level of significance is 0.05. So this area shaded by red lines is 0.05, and therefore this critical value is denoted by chi-square 0.05, and this shaded area is rejection region. So if our calculated value of test statistic is in rejection region, we will reject the null hypothesis, and this area is called non-rejection region, area to the left side of this critical value. So we are considering values of chi-square on horizontal axis, and now we are interested in this point chi-square 0.05, such that area to the right side of this point is 0.05 and degrees of freedom are 14. So to find out this critical value, we will use chi-square table with area to the right of this point as 0.05, that is alpha equal to 0.05, and degrees of freedom equal to 14. So now we are searching for chi-square value corresponding to 14 degrees of freedom and 0.05 area in the chi-square table. So here column headings are nothing but area to the right of critical value, and we are interested in 0.05 area. This left column corresponds to degrees of freedom. Our degrees of freedom are 14, so we go down up to 14 here. So this row corresponds to 14, so we go in this row up to 0.05 area. Here also we go down up to this 14 degrees of freedom row, and we find that chi-square critical value is 23.685. This is chi-square critical value for alpha equal to 0.05 and 14 degrees of freedom. So now we write that this is nothing but 23.685. So here we can mention that using chi-square table for alpha equal to 0.05 and degrees of freedom equal to 14, we find that critical value is chi-square 0.05 equal to 23.685. So now we compare calculated value of test statistic with this value. So now this point is 23.685. So we will check whether calculated value of test statistic is smaller than this value or greater than this value. And here our calculated value is 22.94 and this is 23.685. So we can say that calculated value might be somewhere here. This is calculated value of test statistic and it is in non-rejection region, or it is less than this value. So this means we are in non-rejection region, therefore we fail to reject null hypothesis. So here we can mention that here calculated value of test statistic is 22.94 is less than 23.685, which is critical value at alpha equal to 0.05. Therefore we fail to reject the null hypothesis. And what is null hypothesis? Null hypothesis says that population standard deviation of thickness of dice cut from those wafers is 0.50. So we failed to reject null hypothesis. So what is our final conclusion? They are saying that lapping process is acceptable if sigma is at most 0.50, and we fail to reject the null hypothesis that sigma is 0.50. That means we can say that there is no sufficient evidence to reject this claim that this lapping process is unacceptable or unsatisfactory. They are saying that the lapping process is acceptable if sigma is at most 0.50 MIL. So here we fail to reject the null hypothesis, that is sigma is 0.50, that we cannot reject, and therefore we can say that there is no sufficient evidence, there is no sufficient evidence to conclude that the lapping process is unsatisfactory or unacceptable. The lapping process is unacceptable or unsatisfactory. So in this way we can apply hypothesis test for population variance, and you can see it is very easy. You just have to remember the formula for test statistic, and here capital S square is sample variance, small n is the sample size, and this sigma square will be considered as our hypothesized value. Here we are testing the hypothesis that sigma square is 0.50 square. So we take sigma square equal to 0.50 square, and one thing you must note that if it is not given in the problem that population is normal, you have to assume that underlying population is normal, because if underlying population is normal, then only we can say that this chi-square distribution is there. To apply this chi-square distribution, we must say that underlying population is normal. If our random selected is from normal population, then only this random variable is a chi-square random variable with n-1 degrees of freedom. So therefore it is necessary that we must assume that underlying population is normal, and rest of the procedure is same as we are doing in hypothesis testing. First we identify null and alternative hypothesis, then we see what is level of significance, then we calculate the value of test statistic, and after that we find out critical regions or critical values that will give us critical regions, and then we compare calculated value of test statistic with critical values, and after that we conclude or we take the decision that whether to reject the null hypothesis or fail to reject the null hypothesis. So this is all about this session.